Okay, hi everyone. Thank you so much for coming today. We're super excited to have you. My name is Emma. I am the events manager here at KIS, and I just wanted to do a quick introduction before we get into what you are all here for. So as I said, this event is being run by KIS, and if you haven't attended one of our events in the past, I just wanted to let you know a little bit about us. So we're a tutoring company, and we aim to provide as many resources as we can for year 12s because we know just how stressful it can be, as it wasn't too long ago since we were there ourselves. So the way today is going to work is hopefully you've all received an email from me with your booklets. So please have those out, annotate them if that helps, follow along, whatever you need to do to take notes. The rest of the presentation will all be done with Margery, all on her PowerPoint. There will be time to ask questions and have a break. So please interact whenever you feel like you have a question or anything like that you want to say. I'll be sending through some links later in the presentation for feedback and finding a tutor, that sort of stuff. And lastly, if you do want to watch this back, you, as I said, have an email from me. So please just shoot me an email and I'll make sure you get access. We're not going to be putting it on our YouTube because obviously this is a paid event and we want to make sure that it's fair for you guys. So yeah, just send me a little email and I'll get a link for you. So without any further ado, over to you, Margery.
Hi everyone, thanks for coming along to this session. So this is going to be a Back to Basics methods lecture that will run for an hour and a half to just cover some of the basics and do a bit of revision for some of the main topics that you guys will see again in 3-4 this year. So I'll do a quick intro about me. So my name is Margery. I finished VCE back in 2018 and I graduated from Mac Robertson Girls High School. I've had 3 years of tutoring experience so far and I achieved study scores of 45 in both methods and specialist. I'm also currently starting my med degree this year at Melbourne Uni. So that's a brief kind of intro about me. We'll get straight kind of into the session. And so this lecture will be 1.5 hours with the first part being around 25 minutes. And then you guys will get a 5-minute kind of break where you can ask me any questions or anything like that as well. And then our second part will be around half an hour with, again, a 5-minute break before we finish up with part 3 that will run the remaining 25 minutes. And we'll finish at around 2:30. So this here is just kind of a quick overview of what we'll cover in each of the parts. So the first part will cover a bit of functions, graphs, polynomials, discriminant and circular functions before we move into a bit of calculus. And then we'll have a look at a bit of probability, combinations and all of that to finish the lecture off. The next few kind of slides here are just giving a brief overview of the syllabus for Unit 1-2. So we'll cover some of these in today's kind of session, but anything we don't cover, you guys will have a booklet that you've been sent through to kind of do a bit more revision if you want and have a go at some of those questions in there. So as a reminder, this won't cover kind of everything in the course, so you guys can do a bit of extra revision outside using the booklet if you want. And so we'll get straight into it and we'll start off with part 1 of today's session, which is a bit of functions, graphs, polynomials, and circular functions, as well as the discriminant. So we'll start off with graphs. In terms of graphing, our study design lists a bunch of graphs that we need to be familiar with. So this involves both being able to sketch them, also labeling in important points. So some key tips here include firstly working out the asymptotes if they are present. So either our horizontal or our vertical asymptotes. And then plotting them in, we plot it as a dotted line and we label it as either x is equal to something or y is equal to something, depending on whether it's a horizontal asymptote or if it's a vertical asymptote. We know also that our curve approaches but never touches or bends away from the asymptote. So we need, when we're sketching these graphs, we want to make sure that it doesn't kind of curl away from it. And then we also determine the basic shape. So depending on what type of function we're given, whether we're given a square root, a quadratic, a cubic, etc., then we're able to determine the basic shape of the graph before drawing our function in, and then labeling in any x and y intercepts. So we'll have a look now at an example to kind of go through this. So we've got this function here that's asking us to sketch the graph of y equals to 2x plus 3 over x plus 1. So first, to do this, I notice I've got y equals to some kind of fraction looking graph. So to simplify this a bit, I can use my long division of polynomials. So I've got 2x plus 3 divided by x plus 1. And so as a quick kind of refresher, we call our x plus 1 is called our divisor. And so whatever we get in here, so if I wanted to divide this, I now have 2 here because I get 2x plus 2, and then subtract these two from each other to then get 1. So my 2 up the top is called our quotient. And the 1 down here that I'm left with at the end is called my remainder. So once I kind of use this long division to divide through, I can rewrite my function y as now being 1 over, so the remainder over my divisor, plus the quotient, which we can now see is in the form of my y equals to a over x minus h plus k. And we know that this would be a hyperbola for our graph. So to graph this hyperbola, first thing we can determine is if there are any asymptotes. So for our asymptotes, I know I've got x plus 1 equals 0. So x is equal to minus 1. This would be my vertical asymptote. And my horizontal asymptote would be at y equals to 2. So the number on the end over here. After finding the asymptotes, we can then go on to look at our intercept. So starting with the x-intercept, we let y equals to 0. So I can use either this kind of simplified equation that we've found, or I can use the original equation as well. It doesn't matter kind of which one you use, but it might be a bit easier to use the original one because there's, I guess, a few more less steps involved. So we let y equals to 0 to find our x-intercepts. We get 2x plus 3 equals to 0, so x is equal to minus 3 over 2. And so then to find my intercept, I do the same thing. I let x equals to 0, so I get y of 0 is equal to 0 plus 3 over 0 plus 1. Is the same as 3 over 1, so that's just 3. So once I found the asymptotes and the intercepts, I would now plot that to my axes. So I've got x is equal to minus 1, so in dotted lines, we draw in our asymptotes. So we've got x is equal to minus 1 and y is equal to 2. So this over here. I know that I've got a positive hyperbola in the sense that I don't have a negative sign in front of here. So it'll be a graph that will look something like this. So it'll be the top right and the bottom sections of the graph. To plot our actual graph, we can draw in our intercepts. So we've got an x-intercept at minus 3 over 2, so minus 3 over 2, 0, and a y-intercept at 3, so at 0, 3. To draw this in, I can then put this down here. So again, approaching but never touching our asymptotes. So we get something that looks like this over here. And so we've labeled in all the key points, our asymptotes, our intercepts, as well as our general shape of the graph. Yes, that's a bit of sketching as a quick kind of revision on that. Let me know if you guys have any questions through either the Q&A or the chat. But we'll keep going if this is all good. And if I see anything in the chat, we can always go back to that. So yeah, we'll continue on to have a bit of a look at polynomials now. So polynomials, it comes up quite often in 3-4 in terms of sketching and factorizing and all that. So there's two theorems that you guys might have seen before, which is the remainder theorem and the factor theorem. So the remainder theorem provides a fast way to determine our remainder when a polynomial is divided by a linear function. So it's important to note that we can only use this theorem if we're dividing a function by another linear function. So something like x plus 3 or 2x plus 1, etc. And so this theorem states that if a polynomial p of x is divided by ax minus b, then the remainder is p of b over a. So we let whatever we divide equal to 0. We solve for our x, we get x is equal to b over a. And then we substitute this back into our p of x to find the remainder. And our factor theorem is very similar. It kind of follows on from the remainder theorem. So it tells us that if the remainder is 0, then our linear function is a factor of the polynomial. And in order to sketch our cubic graphs or quartics, kind of any graphs with a higher power, we need to find the x-intercepts. So we know that cubics can have, it's just being cut off a bit, so they can have either 1, 2, or 3 x-intercepts. And so when we're sketching, in order to find these intercepts, we would need to first factorize and solve for that. And so the factor theorem allows us to factorize it and to solve for these intercepts. And so it says that if a of x minus b is a factor of p of x, then we know that our remainder, so p of b over a is our remainder. The remainder will be equal to 0. So we'll have a look now again at an example to kind of bring this into a bit of context. So this question here is saying to factorize x cubed minus 2x squared minus 5x plus 6 using both long division and synthetic short division. So I know some schools don't really go through short division. Long division is definitely kind of the more common method we use. And it's also the method that I would kind of prefer when we're doing these questions. But short division is just another way of kind of dividing our polynomials by a linear factor. So we'll go through both methods and you can see that how we go through each. So let's first start off with using long division to factorize our function. So to factorize this, I know that my equation is a cubic. So what I can do is I can substitute in x values to find when y would be equal to 0. So when my remainder is 0, and then I'll be able to find a factor from that. So say I sub in x is equal to 1, just to check. I've got y of 1 is 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6. And that's equal to 1 minus 2 minus 5 plus 6, which is equal to minus 6 plus 6, which is 0. So because here this is our remainder, and the remainder is equal to 0, we know from our remainder theorem that therefore our x minus 1 will be a factor. So x minus 1 is a factor. Because if I let x minus 1 equals to 0, you can see I get x equals to 1, which is the number that I subbed in. So once we've found that x minus 1 is a factor, we can then use long division to divide through by this factor. So the way I do this is I'd write down x cubed minus 2x squared minus 5x plus 6, and that's divided by x minus 1. To do this long division, I look at the first number, the first kind of variable here, which is x cubed. So I know that I need to times x squared by this x to get x cubed. So this top number here, I would write as x squared. So multiplying x squared with this entire linear function here, I get x cubed minus x squared. Subtracting these two from each other, I end up getting minus x squared. Then bringing down my next term forward, so I've got minus 5x here. And again, looking at the first term, so I've got minus x squared. I know that I would need to multiply this x by minus x to get this negative x squared. So on the top here, I'd write down minus x. And so I end up getting minus x squared plus x. And again, subtracting these two from each other, I end up getting minus 6x. Bringing down this to the bottom, I get plus 6. And then again, looking at the first term, which is minus 6x, I know that I need to have a minus 6 at the top to get this minus 6x and then plus 6. And subtract these two, I end up getting 0. So you can see here the remainder here is 0. And that makes sense because we previously established that x minus 1 is a factor. So we won't get any kind of remainder when we divide through. So once we've divided this, we can then rewrite our y as equal to x minus 1 times x squared minus x minus 6. So whatever I end up with at the top over here. So looking at this, I notice I've got a linear function multiplied by a quadratic. So I always want to check to see if I can factorize any further. So the way we can do this is I can use the discriminant. This is something that we will talk a bit about as well. So we can use the discriminant to see whether I'm able to factorize any further. So if the discriminant comes out to be a perfect square, that means I'm able to factorize further. So we can check. So discriminant is b squared minus 4ac. That's the formula for our discriminant. So b squared is minus 1 squared minus 4 times a, which is 1, c, which is minus 6. I get 1 plus 24, which is equal to 25. And so 25 is a perfect square because 5 squared gives me 25. And so because it's a perfect square, I know that therefore I can factorize this further. So to do this, and I've got x minus 1, I can use multiple different methods. If I use cross multiplication to find two numbers that multiply to give minus 6 and add to give minus 1, I know I've got minus 3 and 2. So I can write this as x minus 3 times x plus 2. So this would be my fully factorized form over here. If I left my answer just as this over here, in the actual kind of exam or test, you would lose a mark for this because we haven't fully factorized it. So I always want to make sure that the answer we end up with is in its simplest possible form. And so that's a bit of long division. If we have a look at synthetic short division, the way that we would do this is slightly different to long division. So I'm going to say short division. So what I would do is I would draw out kind of this thing over here, write down the coefficients in front of each term over here. So I've got 1 in front of the x cubed, minus 2 in front of the x squared, minus 5 in front of the x, and the 6 on the end as the constant, take into consideration all the signs. And because I'm substituting in or I'm trying x is equal to 1, I would write 1 over here. So the first thing I would do is bring down this 1 down to the bottom, multiply this by my number over here to then get 1 times 1, which gives me 1. Then I would add these two numbers together. So minus 2 plus 1 gives me minus 1. And again, the number that I end up with down here, I would multiply with this 1. So negative 1 times 1 gives me negative 1. So I'll write that down over here. Again, adding these two numbers together, I get minus 6. And multiplying my minus 6 again to the 1 over here, I end up with minus 6. So I'll then write this number down over here. And finally, again, we add these two numbers together. So 6 minus 6 gives me 0. So I'd get 0 over here. And this last number that we end up with, whether it's 0 or if it's not divisible, then we would actually get another value. This is always going to be the last number. So the last number we get is always going to be our remainder. And so once I've done this division here, I know that this number here is the coefficient of my x squared term. Because we started with the cubic, we would be 1 kind of power down. So this 1 would be the coefficient of my x squared. This would be the coefficient of my x, and this would be the number on the end. And so the way I would write this is I would have x minus 1 times x squared minus x minus 6. And again, we can then further factorize this to get the same answer we got before when we used long division. Let me know if you guys have any questions about any of that as well, either in the Q&A or in the chat. We'll keep going and we'll move on to the next kind of topic, which is talking about the discriminant and number of solutions. So when we refer to number of solutions, we're talking about the concept of discriminant. And this comes in very handy for next year. You'll see a lot of this as well in 3-4 methods. So the discriminant here, this is our quadratic formula when we solve for our x. So this is our quadratic formula. Our discriminant is the term inside the square root. So this in here, the b squared minus 4ac, that's our discriminant. And we represent the discriminant with a kind of triangle over here. So the discriminant tells us a few important things. If the discriminant, so the term inside the square root in our quadratic formula, if that's equal to 0, then we only have one solution or a repeated root. If the discriminant is greater than 0, then we have 2 solutions, or also known as 2 unique roots. Roots is just another way of saying solutions. And so if the discriminant is less than 0, then we have no solutions. And this next point here isn't too important for methods, but if you guys also do specialist, then we know that when the discriminant is 0, we get complex roots instead. But in methods, we would say no solutions with that. So we'll now have a look at a question over here, which is applying the discriminant into an example. So we've got find the value of c such that y equals to 2x plus c is tangent to the parabola with equation y equals to x squared plus 3x. So I know that these two graphs needs to be tangent to each other. So what that means is I have one point of intersection between the two. So I've got a parabola that'll something around like this, and I've got a linear equation line there. And I know that these will be tangent to each other. So they would only have one point of intersection. And we want to find the value of c, which is the number on the end for our equation, for our linear equation. So to do this, I know that to have one point of intersection, to find first, I guess, the intersection, we would equate our two equations together. So we get x squared plus 3x is equal to 2x plus c. Moving everything across to the left-hand side, I get x squared plus x plus c, or minus c, sorry, is equal to 0. To ensure that our equation here has one solution, because we only want one point of intersection, we know that our discriminant needs to equal to 0. So up here we know when the discriminant is equal to 0, we have one solution. So for one solution, we know that our discriminant has to equal to 0. So our discriminant is equal to our b squared minus 4ac, which is 1 squared, minus 4 times a, which is 1, times c, which is minus c in this case. So we have 1 plus 4c. So we need to let the discriminant equal to 0. So we get 1 plus 4c equals to 0. So c is equal to -1/4. And that would be my answer for C. Yes, that's a bit about discriminants and number of solutions. We'll now continue on to have a bit of a look at circular functions. So for circular functions, it's really important that we know our exact values and also symmetrical properties of our trig functions. This table here shows some of the exact values we get when we have sine, cos, and tan for our various angles. So pi over 6, pi over 4, pi over 3, and pi over 2. If you guys kind of don't remember or need a bit of refresher, it's always good to have a look at that and remember some of those values, because you'll see it a lot this year as well. So yeah, some kind of properties and formulas. We know that tan of x is equal to sine of x divided by cos of x. And we've also got sine of pi over 2 minus theta is equal to cos theta, and cos of pi over 2 minus theta is equal to sine theta. So the way that I remember this is if I draw out a unit circle, I know that this vertical line here is my pi over 2. And if I have pi over 2 minus theta, then I will be in this first quadrant over here. And we know that in this first quadrant, both sine and cos are positive. So because I've got pi over 2 minus this angle, I know that I would get the opposite trig function. So we started with sine, we now have cos, and it'll be cos of our angle theta. But it would be positive because I know that sine is positive in this first quadrant. Same thing for this. When we have pi over 2 minus theta, I get sine of theta, so the opposite kind of function there. And I have positive sine theta because cos is positive in this first quadrant. And again, we've got this formula over here, which is x squared plus, sine x squared x plus cos squared x is equal to 1. And so this here is talking about the unit circle. So a way to remember this is, so ASTC, all students to class. So we start at kind of this positive quadrant in the axis, and then we move across in an anti-clockwise direction. So we get ASTC over here. Yeah, so we're going to now move on to a bit of solving our trig functions. So this tends to be an area that a lot of students I find a bit tricky and challenging in. So it definitely can be quite tricky. So it's good to adopt some kind of systematic steps. So these steps here, you don't need to follow too rigidly, but I think it's a good guide to kind of help you when solving any type of kind of trig function. And so the first thing we do is we rearrange for a simple equation. So what that means is we ensure that the function that we have on the left-hand side doesn't have any coefficients or any numbers in front of it. And so if it does, then we need to divide through and do a bit of kind of calculation and rearranging with that. The next thing we do is we find our base angle using our exact values. And then we look at the sign of our angle. So this would be given in the question in terms of whether we have positive or negative. We then draw the unit circle and solve for our angles. After that, we add on as many periods as required based on the domain that we're given. And so we'll have a look at this over here, which is talking a bit about sine of 2 theta is equal to negative 1/2. And we want to solve for our theta, given that theta is between 0 and 2 pi. So to do this, the first thing we do is we rearrange here for a simple equation. In this case, you can see my sine of 2 theta is already by itself. There's no numbers added on the end or multiplied to it. So it's already been rearranged into the simplest equation already. The next thing we do is we then find the base angle. So to find the base angle, I ignore kind of the angle inside the trig and also any of the signs. I purely look at what function I'm given and the actual number. So I'm given a sine and I have that equals to 1/2, ignoring the negative in front of it. So I know that from my exact values, my base angle would be pi over 6, because sine of pi over 6 gives me 1/2. The next thing I would do, which is not really listed up there, but because our angle inside the trig function is 2 theta, and the domain we're given is theta, we then need to find the domain for our angle, so the 2 theta. We know that since theta is between 0 and 2 pi, so since theta is between 0 and 2 pi, I know that my 2 theta would be between 0 and 4 pi. So once I found my domain for the angle inside the function, I then look at the sign that I'm given. So I see I've got a negative over here. Once I've determined that, I can draw out my unit circle and solve my angles. So draw out my unit circle. I know that sine is negative in the third and the fourth quadrant, so ASTC. Sine is negative here and here. And these angles over here are pi over 6, so our base angles. So once we've found out the quadrants which they're negative in, I write down 2 theta, so whatever angle is inside the function, that is equal to. So I can first go into here, so into this third quadrant. I know this would be pi plus pi over 6 for my angle. Then if I move on to my fourth quadrant over here, this would be 2 pi minus pi over 6. Because I know that my 2 pi is always positive, I don't need to go in the negative direction. So I don't need to go kind of here and say this is negative pi over 6 and this is negative 5 pi over 6, purely because we know it's between 0 and 4 pi. So it'll all be positive. Once I've kind of found my positive angles in the 2 quadrants there, I can simplify this a little bit to get 7 pi over 6 and 11 pi over 6. So the next thing I would do is I would look at my actual domain and see if I can add on any more periods. So this is dependent on our actual domain. So the domain for us is the 2 theta. So this is 0 to 4 pi. So because we went in the positive direction and we're talking about positive angles, I want to add on 2 pi to each of this to see if it still lies between 0 and 4 pi. So if I add on 7 pi over 6 plus 2 pi, and now I end up getting 19 pi over 6, which is less than 4 pi. So this is another solution I've got. Then I look at my 11 pi over 6, and I also add 2 pi onto that to see whether it still lies in the domain. So I get 23 pi over 6, which again is still smaller than 4 pi, because 4 pi is 24 pi over 6. So then I would also have that as a solution. You can see now I can't add on any more kind of 2 pi's onto these 2 solutions, because that'll be a lot larger than 4 pi and it will be outside our domain. So these are all the solutions that I've got. Finally, because of course we're trying to solve for theta, I can divide through by 2. So I get 7 pi over 12, 11 pi over 12, 19 pi over 12, and 23 pi over 12. So that's a bit of solving for our circular functions. I'm noticing the time, so I know we started a bit of intro and all that. So we'll finish off. This last part here is a bit of sketch, and that's the last question for this part. So we'll have enough time because the next section won't be, I guess, as time consuming in the sense. So we'll move on to have a bit of look at sketching now. So for sketching, we know that the graph of our trig function, if we have something like this, f of x is equal to a sine n times x minus h plus k. Our period is given by 2 pi over n, where n is the number in front of my x. Our amplitude we determine as a, so the number that's in front of my trig function, whether it's sine or cos. And looking at this, we also know the graph is shifted to the right by h, because if I let nx minus h equals to 0 to see what the horizontal translation is, I get x is equal to positive h. So it's shifted to the right by h units. And we've also got a plus k on the end over here. So we've got a shift of k units up. So in terms of actually sketching these graphs, again, these can be quite complicated with all of these kind of transformations and all that. So it's good to take some systematic steps when we're dealing with these graphs. So the first thing we can do is we can determine the values for the period and the amplitude. Once we've done that, we can draw a dotted line at the vertical shift position. And I'll explain what that means with the example that we've got. And then we can also label in our maximum or our minimum line. Once we've done that, we can mark off one full period, then plot in a few key points. So any turning points and maximum minimums, and any points where the curve intersects our dotted line. This dotted line is referring to our vertical shift position. Once we've done that, we can join the points up and repeat to give more periods, depending again on our domain. So we'll have a look at this example over here, which is saying y is equal to 3 sine 2 times t minus pi over 4, where we've got t's between pi over 4 and 5 pi over 4. So to draw this, trig functions are really the only type of functions that I really rely on transformations. All kind of other graphs such as exponentials, logs, hyperbolas, I prefer to use the more like asymptote, intercept, and kind of general shape method. But for trig functions, I find it easiest for students to use a more transformations kind of method. So the first thing we do is we find our amplitude before even sketching it. So the amplitude we know is equal to 3. Then we can find our period. Our period is 2 pi over n, where n is the number in front of the t in this case. You can see we've got the variable as t instead of x. That's okay. So we know it's 2 pi over 2. And that's equal to pi. We know this graph here has the same shape as my y equals to 3 sine 2t. But our graph is translated pi over 4 units to the right. because when I let t minus pi over 4, when I let this, the 2 at the front, when I let this whole thing equals to 0 to find my horizontal translation, I get t is equal to pi over 4, and it's positive pi over 4. So I've shifted it to the right by pi over 4 units. Then to draw in my graph, I would draw in my t-axis and then my y-axis. I know that my amplitude is 3. There's no vertical translation in this case. So my maximum value would be 3 and my minimum would be -3. So then I would draw in dotted lines along here. And we know that we're going between pi over 4 and 5 pi over 4. So before kind of taking into consideration our domain, I first plot in my 1 period. So this is pi, so between 0 and pi. Then I've got halfway between there is pi over 2 and pi over 4 and 3 pi over 4. So I got 3 pi over 4 by adding pi over 2 with pi and dividing by 2 to find the midpoint between those two values. Once I plotted that in, I know that I can draw in first my base graph, so the general kind of graph, the simple one, before we actually draw in our final graph with the translation. So to draw in 3 sine 2t, I know starts at 0, then gets to a max, and then 0 again, minimum and 0. So this would be what my graph looks like. And I draw this in dotted lines just because it's not our actual graph. And so we know that our graph is the same shape as this, just translated to the right by pi over 4. So now this point here would move across to here, and I'd have a maximum at pi over 2, a 0 at 3 pi over 4, and a minimum now at pi. So I'd get this graph that looks like this. Final thing I do is I check my domain to see if I've taken the whole domain that we're given. So we're given pi over 4 to 5 pi over 4. I notice that I'm already starting at pi over 4, so that's good. But we're ending at pi just from the graph that I've drawn here. So I know that I want 5 pi over 4. So looking at this, I can see each of these increments here differ by pi over 4. So the next increment from pi would be 5 pi over 4. And I know that because this is one increment, this would be at 0. This would be at 0, and I can just join the dots like that. And so this would be how my graph looks from here. Yeah, cool. Do you guys have any questions about any of this? Let me know if you do in either the chat or the Q&A. So if you guys want to break, it is up to you. I know we're running slightly over time, but that's okay because part 2, I think, won't be as lengthy. But if you guys want to break, let me know. We can have a 5-minute or a couple of minute break. If you guys have any questions as well, you can also let me know through the chat.
I'm just getting a couple of questions coming through on the direct message to me. So one has asked if for studying, what were your best tips and tricks for preparation for SACs and the exam?
Yeah, that's a really good question. So for both the SACs and the exams, something really important is to know kind of how to use your KIS calculator. So especially more applicable to exam 2, but for your SACs as well, knowing kind of how to be fast and the different functions on your calculator would really help in terms of working out and saving a lot of time as well to ensure that you're able to finish the paper. In terms of actual preparation, though, I would say definitely once you've kind of learnt the content, you've had a bit of practice with the textbook questions, have a go at some of the past exam questions. So even though you haven't covered a lot of the topics yet, you can always go through some kind of commercial exams or past exams to pick out the questions that relate to the topics that you'll cover in your SAC. So if you're doing functions for your next SAC, then have a look through some of those kind of questions and pick those out and have a go at that. Because I think those kind of questions would be most representative of what you would actually see on the exam and also in your SACs as well. Yes, I think that's something that I've done that I found quite helpful.
Yeah, perfect. That sounds really good. And then the next question here is, do you think it is worth keeping specialist if I'm not that good at it, or should I just stick to methods?
Yeah, I think so for this one, it is definitely kind of up to you. So I feel like, so if you're finding specialists a bit challenging, it is quite a challenging subject, but it's also easy to improve in the sense that once you've understood some of the basic concepts and had a bit of practice in, it can really help kind of boost your confidence and also your understanding in different types of questions. But if you do feel like, I guess, if you're really finding it challenging and you're not really enjoying it that much, then it is up to you to see whether you want to continue or not. But I personally really love Spec, so I think it's a good subject to have if you're interested in it and if you're keen to kind of improve. Yeah.
Okay, perfect. I don't think we're getting any more questions through, so I'm happy if you want to go on to your next content block.
Yeah, sure. We'll continue on then and move on to a bit of calculus. So for calculus, we will start off with a bit of average rate of change. So the average rate of change between 2 points on a graph is simply the gradient between those 2 points. So when we're talking about average rate, we're talking about gradient between 2 points. And so what this next kind of paragraph is saying is that the average rate of change for a function f of x between a and b for our x values is given by f of b minus f of a over b minus a. So all this is really saying is that if I have a graph here where I've got a between a and b, and I want to find the average rate of change, I know that this is just my gradient. So it'll be f of b, which is the y value when I substitute in b, and f of a is the y value when I substitute in a. So what I'm really using is the gradient formula. So if you guys remember, we've got y2 minus y1 over x2 minus x1 as our gradient formula. And so when we use this, we're able to find our average rate of change between 2 points. For instantaneous rate of change, so the instantaneous rate of change is the gradient at a particular point on a graph. So to figure out the instantaneous rate of change, we first find the derivative of the function and then substituting our particular point to find the gradient of that function at that particular point. So if we have y is equal to f of x, and we want to find the instantaneous rate of change at x equals to a, then we find the derivative, so we get f dash of x, and then we substitute in our a, so that we get f dash of a over here. Yeah, so that's a bit of kind of instantaneous rate of change compared to average rate of change. We'll now have a look at a bit of differentiation. So a few general rules of differentiation. The overall kind of rule for our function, if it's in the form of kx to the power of n, we would then have times by the power. So essentially bring down the power times that and then subtract 1 from the power when we have something in the form of kx to the power of n. And so these few rules down here are saying that if I have k, which is a constant, then the derivative of our constant is equal to 0. Which if you think about it a bit graphically, is if we have k a constant, which is y equals to k here, it'll be a horizontal line. And we know that the gradient of a horizontal line is 0. So the derivative of a constant would then be 0. Similarly, we have derivative of a times f of x. I can bring out the constant a to the front and derive f of x and multiply that by my a. So this is only when a is a constant though. If we have two functions added together, so f of x plus g of x, and we wanted to find the derivative of that, we can split it up into these two parts. So derive f of x and then add the derivative of g of x. And the sign here is plus here. If it was minus, if it was f of x minus g of x, we can do the same thing. It would just be minus between the two. And this last one here is saying if we have the derivative of x to the power of n, we bring down the power. So we multiply the power, bring it down. We have n times x to the power of n minus 1, subtracting 1 from the power. So it's a general rule that we would have seen quite a bit of. We'll now move on to an example down here, which is a fairly quick one. So it's a bit of revision. If we wanted to find the derivative of y equals to 2x cubed minus 2x plus 1, I know that all of the terms I've got in here are in the form of course, the 1 is just a constant. So all of the other terms are just in the form of kx to the power of n. So in order to find the derivative of this, I know that I bring down the power and I subtract 1. So to do this, we got dy dx, the derivative, is equal to 2. So I write it like this, so is equal to 3 times 2x, and then minus 1 from the power, minus 2 times x, and then 2 minus 1, so minusing 1 from the power. And we know that when we derive a constant, the 1, we get 0. And so simplifying this, I get 6x squared minus 2x. And that would be my answer for that one. So yeah, so a bit of simple differentiation there. We'll move on now to a bit of stationary points. So in terms of stationary points, this relies on differentiation as well. So a stationary point is a point on the graph where we have 0 gradient. And there's 3 different possibilities that we could see. So we can either have a local max, a local min, or a stationary point of inflection. If it was a local max, it'll look something like this. If it was a local min, it'll look something like this. If it was a stationary point of inflection, then the graph would look something like that. So these are our 3 different possibilities that we could get. In terms of the absolute maximum and the absolute minimum, this just refers to the maximum or the minimum value of a function over its entire domain. Whereas local max and local min only refers to stationary points. So when the gradient is equal to 0. But our absolute maximum and our absolute minimum is when we consider the whole domain and see what the actual lowest y or the highest y value is. So for how we actually go about finding our stationary points, we can find our stationary points by solving for the gradient being 0. So when we let dy dx equals to 0. In order to find the nature of stationary points, so this is kind of what type of stationary points we're talking about. Nature refers to what type. So whether we have a local max, a local min, or a stationary point of inflection. So that's what we're doing when we're trying to find the nature of our stationary points. So once we've solved for the stationary points, we found out what the coordinates actually are, we can determine their type or their nature. To do this, we can use 2 different methods. So we can either sketch the graph, so drawing the graph out, seeing what it looks like, whether it's a max, a min, or a stationary point of inflection. Or we could also use our gradient sign test. So this tends to be the preferred method because a lot of the time our graphs might be really difficult to sketch. And if you don't have your calculator on you, then doing it by hand would be really tricky. So using our gradient sign test, what we do is we find the gradient immediately before and immediately after it. And we can use that to determine what type of turning point or stationary point we have. Now we'll go through an example in terms of how to actually apply this type of test with this question down here. So we've got the graph of f of x is equal to this function here. And this has stationary points at 1, -7/6 and 2, -2, 10/3. So those are our 2 coordinates for our stationary points. And we want to use the gradient sign test to determine the nature of these. So we notice we've got 2 different stationary points. So that means we want to test both of those stationary points to see whether they're a local max, a local min, or a stationary point of inflection. First thing I do is I find the derivative of my f of x first. So I've got x squared plus x minus 2. So bringing down the power and subtracting 1 from the power. Then what I will do is I will draw out my table. So we could use one whole table for both points, or we could use 2 tables, one for each point. It is up to you. I find it easier to use just a table for each point for our stationary points. So if we have x, then we have f dash of x down here, and we label this next part our slope. So this would be our table here. where we have 3 values. So this middle value here would be the x value of my first stationary point that I'm testing. So let's just say I test this point over here first. Then I take a point slightly less than 1, so I'll take 0, and another point slightly greater than 1, which I'll say 2. And you can take any number, just not too large, because then we might kind of go a bit over the stationary point. So we might kind of miss the stationary point if there's another one between those 2 x values. So a value that's slightly smaller and slightly larger than the value we have for our stationary point. We then substitute that into our f dash of x, our derivative function. We know, of course, when x equals to 1, the derivative is 0 because that's a stationary point. And so when we substitute in 0, we get -2. When I substitute in 2, I end up getting 4. And so our slope is essentially what the line would look like. Because we have a -2 here, we've got a negative gradient. So it looks something like this. This is 0, so it would be a horizontal line, and 4 is a positive line over here. So basing this on here, we know that at this point, so at 1 minus 7/6, I have a local minimum. And I do the same thing for my other table. So let me, rather than drawing it out, So again, we draw the same table, but this time we choose different points. So in this case, I've got -2 as my stationary point for the x value. So I take a point smaller than that, which is -3, let's say. I take a point slightly larger, which is -1. Substitute it into my f dash of x. I get 4, 0, and -2. And my slope would therefore be this horizontal and then a negative here. And so again, my slope graph type will look like this. So I know that at -2, 10/3, I have a local maximum over here based on kind of our slope. Yeah, so that's how we would go about determining the nature of our stationary points once we've actually found it. So now we'll have a look at a question on applications with stationary points. So in terms of application problems, we want to maximize or minimize something. And there's quite a few different kind of real life applications for this. So in terms of how we do this, we first solve for our stationary points, and then we determine their nature to see whether we are able to maximize or minimize that. So I'll have a look at an example to kind of put that into context. I have this question over here, which is saying the height of a projectile at time t is given by this. So h is my height, and I want to find the maximum height that the projectile attains. So the first thing I do is I know that because I want to find the maximum, I'm referring to a stationary point. So I can find the derivative of my h. So I get dh dt is equal to 10 minus 9.8t. I let dh dt equals to 0. I get 10 minus 9.8t equals to 0. And if we solve this on our calculator, we get t is equal to 1.02, assuming we're talking about seconds. So we know that there is a stationary point at t is equal to 1.02. So then to figure out the actual height at that point, I can substitute in my t when it's 1.02 into my h. So I get 10 times 1.02 minus 4.9 times 1.02 squared. So again, putting that onto our calculator, we get 5.1 meters there. And so 5.1 would be the highest, would be the maximum height that I get. So that's a bit of the applications for our stationary points. We'll continue on then to have a look at a bit of anti-differentiation. So we know that we can go from a function f of x to f dash of x by finding the derivative. But if we're given the derivative function f dash of x, we can also find the function f of x by using anti-differentiation, which is the reverse process of differentiation. So we'll look at a few different rules in terms of how anti-differentiation works. And you'll see a lot more of this in 3-4 methods as well. So if we have something like x to the power of n and we wanted to integrate or anti-differentiate that, then what I do is I add 1 to the power. So the general, I add 1 to the power, and then I divide by the new power. So I can see here I've got x to the power of n plus 1 now, and I divided by this new power n plus 1. And whenever we anti-differentiate, we have a plus c, so a constant on the end. And so for this next one here, so something slightly more complex, if we have ax plus b to the power of n, in order to anti-differentiate this, I have, so ax plus b, I do the same thing. I add 1 to the power, so n plus 1, divide by the new power. But this time, because I don't have something in the form of kx to the power of n, rather I've got ax plus b in the brackets, I would then need to multiply it by 1 over the derivative of whatever's inside the brackets. So if I derive ax plus b with respect to x, I get a. So I need to multiply it by 1 over a. Very similar, if you guys remember, for differentiation, where we apply the chain rule, we multiply by whatever's inside the brackets. But this time we multiply it by 1 over that. So a bit of kind of reverse for anti-differentiation and differentiation. And we end up getting something like this. And this next 2 points are fairly similar for differentiation. So when we have the anti-differentiation of f of x plus g of x, it's the exact same as when we differentiate it. We can split it up into these two and have a plus in between them. If I had minus between them, again, I would have minus between the two integrals there. And if I have a function a times f of x and I wanted to anti-differentiate that, then I can bring the constant out to the front and just anti-differentiate my f of x. So those are a few different rules in terms of anti-differentiation. We'll have a quick look at now kind of why we have the plus c on the end. So we know whenever we anti-differentiate, we'll always have a plus c on the end. So really at the end of like all of these, at the end of this here, we would also have a plus c over here. And the reason is because if we think about it, if we wanted to derive, to differentiate x squared, I know I get 2x. If I wanted to differentiate x squared plus 2, I also get 2x because I know when I differentiate the constant here, I get 0. So if I wanted to then say that the integral of 2x, so the integral of 2x dx, so if that's x squared or if that's x squared plus 2, because both of them when I differentiate it gives me 2x. So that's why when we integrate or we anti-differentiate 2x with respect to x, I would write x squared plus c, where c is a constant. So we can add any number onto the end of that, and it'll still give us 2x when we differentiate it. So if I have x squared plus 1, x squared plus 10, or x squared plus 100, if I differentiate all of these, I always get 2x. So that's why we include the plus c on the end to cater for that. We'll now look at a quick example in terms of anti-differentiation and how we would use it in practice. So if we have f dash of x is equal to x squared plus 2x plus 3, and we know that f of 0 is equal to 1, and we want to find f of x, we know that I'm given f dash of x and I want to find f of x. So this is an anti-differentiation problem. So my f of x is equal to the integral of f dash of x with respect to x. And so I know that my f dash of x, the derivative is x squared plus 2x plus 3 dx. So to integrate that, I get, so plus 1 to the power divided by the new power, 3x, and I get a plus c on the end. To find what this c value is, we always do want to find what it is when we're given an extra kind of piece of information here. So we know that f of 0 is equal to 1. So this tells me that when I substitute in x equals to 0, I get c, and that is equal to 1. So since c is 1, I know that therefore f of x is equal to a third x cubed plus x squared plus 3x plus 1. So yeah, it's a bit of applications in terms of anti-differentiation. And again, let me know if you guys have any questions in the chat and everything. We'll continue on and have a look at a bit on definite integrals. So for our definite integrals, we know that this is also called the fundamental theorem of calculus. So when I want to anti-differentiate f of x from a to b, so because I've got two values over here, this is called a definite integral. And so when I anti-differentiate that, I end up getting this big f of x. So this is notation here is just saying that this big f of x is really just equal to the integral of f of x. So essentially when we've integrated our little f of x, we get this big f of x. And again, we've got from going from a to b. So going from a to b over here. And that is equal to f of b minus f of a. So substituting in those two terminal values. And of course, f of x is any antiderivative of little f of x. Okay. So yeah, this directly relates to our kind of areas under the curve. So when we're talking about this integral over here, so going from a to b of f of x, when we find that integral, that's the signed area between the x-axis and our graph for our values being between a and b. So for example, if this is a, this point here for our x value, and this is b over here, then when I say that when I use kind of the integral of a to b of f of x, you can see I'm finding the signed area because I'm not really considering the fact that this area over here is negative. If I wanted to find the total area, then of course I would need to kind of cater for that and do a bit of manipulation with this part over here because this is below the x-axis. And so we know that there is a difference between signed area and total area. Signed area doesn't kind of take into consideration the area beneath the x-axis or above the x-axis. It just really finds the integral from the two kind of limits and evaluates that. Whereas the total area, we want all the areas to be positive. And so when we add up the integrals, we end up getting the entire area. So this whole area over here plus this area down the bottom over here. So making this area here positive when we find the total area. But we'll look at an example to kind of go through that as well. And so for the total area under the curve, we know that if we wanted to find the total area, let's say this is 0, and this is 2, and this is 4. Using this graph here as an example, to find the signed area, so our signed area would be just the integral of 0 to 4 of my f of x dx. So this would be my signed area, ignoring the fact that this area here is negative and all that, just taking the integral directly from the lower limit up until the upper limit. If, however, though, we wanted to find the total area, this would be slightly different. So I know that my total area would be from 0 to 2 of f of x dx. And so this is this area over here, which is above the x-axis, so that's positive. I would then also need to consider this next area over here, which is negative. So because I know that this area is below the x-axis, when I take the integral from 2 to 4 of my f of x dx, I know that this thing, when I find the value of it, will be a negative answer because it's below the x-axis. But we're talking about total area, so we can't have a negative area. So in order to make this integral over here a positive, what I can do is I can include a negative out the front. Because I know if I have a negative and this answer here gives me a negative, then I would have a positive between the two. So now this is where the negative comes in over here. Yeah, and in this case, this down here is just kind of showing us that because the graph is symmetrical, we can just find the area between 0 and 2, which is our positive region over here, and multiply that by 2, because the other region down here is the exact same. Yeah, so to finish this section off, we'll have a bit of a look at integration. So for integration and kind of graphing and all of that. So if we've got a question over here that's saying for the graph y is equal to x squared minus 4, we want to find the total area bound by the graph and the x-axis between x is equal to 1 and x is equal to 4. So to do this, whenever I'm given an area question, I always like to sketch a graph just to see kind of which regions we're talking about and which areas are kind of negative and positive and all that. So to do this, I know I've got y is equal to x squared minus 4. That's the same as x plus 2 times x minus 4, sorry, x minus 2, using my a squared minus b squared kind of formula. And so to sketch this graph in, I know it'll look something like this. I've got x, y, minus 2 and 2. So I've got a graph that looks something like this. And so we want to find the total area of bound by the graph in the x-axis between x is equal to 1. So say this is x is equal to 1 and also x is equal to 4. So the regions that we want to find are this area over here and this region over here. So to find this, the first thing that I notice is that this area over here is a negative area because it's below the x-axis. So in my calculations, because we're asked to find the total area, I would need to do a bit of manipulation to kind of cater for that. So to find the actual total area, I know that total area is equal to the integral from 1 to 2 of my f of x or y, which is x minus 4 dx. But this region is the negative area that we're talking about. So in order to make this positive, I know that I can put a negative sign in front of that. Alternatively, we could have also changed the terminals. So if we go from 1 to 2, in order to make this kind of a positive from there, we can have 2 to 1. So that's also another possibility if you didn't want to add a negative in the front. So we've got negative that plus our integral from 2 to 4 of my x squared minus 4 dx. And so this is plus here because this region over here is positive. So we don't need to kind of do anything to it. So to do this, we know that we can integrate. So I get negative of 1/3 x cubed minus 4x. So adding 1 to the power, subtract, dividing by the new power, get from 2 to 1 plus 1/3 x cubed minus 4x from 2 to 4. And so we know that to work this out, we substitute in each of the terminal values. So I have negative of 2 cubed, which is 8, so 8/3 minus 4 times 2, which is 8. And then subtract everything when I substitute in x is equal to 1. So I get subtract 1/3 minus 4. Then plus, so 4 cubed is 64/3 minus 16. So substituting in x is equal to 4. And then minusing everything again when I substitute in x is equal to 2. So I end up getting 8/3 minus 8 over here. And so I won't go through the actual kind of arithmetic and all that, but once you simplify, we end up getting 37/3 square units for our total area. If we kind of didn't cater for the fact that this would have been a negative area, our answer would have been a lot smaller because we would have had a positive area minus kind of the negative area and had a smaller answer for that. Yeah, so that concludes part 2 of this, which is a bit of calculus and all that. Again, if you guys have any questions, feel free to send it through in the chat or the Q&A. At the time, if you guys want a break or if you guys have any questions, I'll spend a few minutes on that.
I think we should just power through to get the last section done. We only have 20 minutes left and then we can do questions at the end if people want to stay behind.
Yeah, sure. Sounds good. Sounds good. Cool. We'll continue on then. So with the last part, which is a bit on probability. So probability, we'll do a quick kind of recap on some of the key terms here. So random experiment refers to an experiment with a random outcome. So for example, taking out a jelly bean from a jar. The outcome is the result of our random experiment that we observe, such as, for example, the color of a jelly bean. Our sample spaces refers to all the possible outcomes. So all the possible colors for our jelly beans. And the event refers to a single outcome that we're trying to kind of find the probability for. So we'll have a look at mutually exclusive events. Mutually exclusive events refers to when A and B, so two events A and B, when they can't occur together. In other words, the probability of A and B is equal to 0. So there is no intersection between A and B. So this is what mutually exclusive means. In terms of independence, we know that A and B, two events, are independent if the occurrence of one doesn't affect the likelihood of the occurrence of the other. So if something occurred beforehand and that doesn't affect the probability of something else occurring, then we say that the two events are independent. And to actually test out whether the two events are independent or not, we can use this formula over here. So if A and B are independent, then we know that probability of A and B is equal to the probability of A times the probability of B. If this was not equal, then we say that events are not independent or they are dependent. We'll now have a look at a bit of Venn diagrams. So when we say probability of A, we refer to the probability of event A occurring, and probability of B is probability of B occurring. So if we have probability of A and B, this is a probability that both A and B occur. So this intersection region between A and B, the overlap there. If we have probability of A union B, this is a probability that either B or A occurs. So it can be either A or it can be B. So this region over here in the Venn diagram. The next kind of rule we're going to talk about is our addition rule. So the addition rule probability is stated over here, which is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A and B. So we know that when we're talking about A union B, this refers to A or B. So if we shade this region in our Venn diagram, we know that A or B looks like this over here. So if we have probability of A, which is this, and we add probability of B over here, so this is the whole of A, and we add the probability of B over here, you can see there's an overlap between the intersections. So when we add A and B, we actually get two intersections, but we know that A union B is A or B. So that only includes one intersection. And so that's why we need to subtract A intersection B from that in order to have A union B. Yeah, so that's a bit on the addition rule. We'll now have a look at this example over here, which is adapted from a VCA question. So it was the 2013 exam 2 question over here. So we've got for events A and B, probability of A and B is equal to P, probability of A dash and B is equal to this, and the probability of A and B dash is equal to this. And so if A and B are independent, we're told we want to find the value of P. So we know that in order to test whether the two events are independent or not, we test whether probability of A times probability of B is equal to the probability of A and B. So in this case, we know that probability of A and B, they give us as P. So this would be P over here. So we don't know what probability of A and probability of B are. So what we can do is we can draw a two-way table to find out those values. So the way we draw this table is I have two events A and B, so I can write down A and A dash, B and B dash over here. So then we get this over here. And so looking at this, I know that all probabilities add up to 1, so I have 1 over here. Probability of A and B is P, so I label this in probability of A dash and B, so this one over here is P minus 1/8. Probability of A and B dash is 3P over 5. And so that's all the information that we're given from the question. We know that probability of A would then be P plus 3P over 5. So that's equal to 8P over 5. So this would be what this bottom space would be. So 8P over 5 when I add up these two together. And to figure out my probability of B, this is what would be over here, because this is my B. So I've got P plus p minus 1/8. So I end up getting 2p minus 8. Oh, minus 1/8, sorry. And so we don't actually need to fill out the rest of the table because what we want to find was probability of A and also the probability of B, which we've already found over here. So we know probability of A is 8p over 5 and probability of B is 2p minus 1/8. And that is equal to my P. So then to find the value of P, we can chuck that onto our calculator because this is a exam 2 multiple choice question. So when we solve this on our calculator, we end up with two answers, 0 and 3/8. Only one of these answers are valid though, because if P is equal to 0, we know that if we substitute this back into kind of the values that they give us, we get 0 minus 1/8 for my probability of A dash and B. This gives me minus 1/8. And I know that, of course, my probability has to always be positive. So therefore, 0 won't work. And the only value that works is P is equal to 3/8. So always checking when we have two solutions, whether both of them would be valid or not. Continue on then to have a look a bit on conditional probability. And so this was a C for our answer. For conditional probability, we know that this refers to knowing something that has already occurred will change the probability that another event occurs. So for example, if I roll a die and I tell you that it's an even number, then what's the probability that it's a 4? So this would be different to just asking us what the probability that I roll a die and it's 4, because we already know that something else has occurred. So this formula down here is our conditional probability formula. So the probability of A given B is equal to the probability of A and B divided by the probability of B. This probability up here, it would be this up here. And so, yeah, the next thing here is probability tables. So we looked at that in our multiple choice question just before. So there's a bit of kind of trying to draw up the events. So if we have two events, we're able to use this table and technique to solve various questions. Only when we have two events, so if we have more than two events, we won't be able to use that table. That table is sometimes called a 2A table or a Karnoff map as well. So now we'll have a look at probability table example. So we've got this question over here, which is saying in a maths lecture hall, 45% of students are K-pop fans and the rest like rock. And 40% of students are boys. So 40% of the students are boys. It is known that 10% of students who are girls like K-pop, and the student is chosen at random. I think there's just a bit of a typo over here. This should be rock. So what is the probability that it is a boy liking rock music? So to do this, I know I've got two events. So I've got either K-pop or rock or no K-pop, and then boys or girls. So I'm able to use a probability table to figure this out. So to do this, I can label this as B for my boy and B dash for my girl. So B dash here. And we've also got K-pop or K dash. So K dash is really just our rock, but it's a bit easier to represent it like this. So then to figure this out, I know I can draw up this table over here. And I have always 1. So this is always the 1 down here because all of my probability has to add up to 1. So now labeling in the information that we're given, we're told that 45% of students are K-pop fans. So K would be 0.45. The rest like rock, and 40% of the students are boys. So my boy here down this column would be 0.4. And then we know 10% of the students are girls who like K-pop. So girls and K-pop would be here. And so this is my 0.1 over here. And we're asked to find the probability that we choose a boy who likes rock. So let's fill out our table first. We know that everything across here needs to add up to 0.45. So I'm missing 0.35 over here. And again, these two here needs to add up to 0.4. So I get 0.05. This here would be 0.6 because again, this needs to add up to this number over there. And so this is 0.5 and I get 0.55. You can see 0.4 plus 0.55 gives me 1 as well, which is down here. So once I completed the table, I can see that the probability that they're asking us to find is that it's a boy who and they like rock. So, and they don't like K-pop, so K dash. And using the values that we found, we can see here, this is this value over here. So B and K dash, which is 0.05 from our probability table. Yeah, so an example of how we can use our probability table to figure out these types of questions. We'll continue on now to look at something a bit different, which is talking about total probability. So we know the law of total probability is given by this formula down here. So probability of A is equal to probability of A given B. So this symbol here is called given, multiplied by the probability of B, plus probability of A given B dash multiplied by the probability of B dash. So what this actually means is if I've got jelly beans and jelly babies in a jar, and I have both green and blue ones, then the probability of me picking a jelly baby would be the probability of having a jelly baby given it's green multiplied by the probability that we have a green color, plus the probability of my jelly baby given that it's blue multiplied by the probability that we choose something blue. So that's a bit of our total probability. We look at this next concept here, which is a bit on tree diagrams. So a bit of revision on how we draw out our tree diagrams. So in this example here, we've got a container contains 3 red shorts and 2 blue shorts, and 3 shorts are picked out from the drawer, and these are not replaced. So in this case, we know this is referring to a question that is talking about without replacement. We then want to draw a tree diagram that shows all of the outcomes possible. So we know to do this, I can draw out something like this. So red and blue are my 2 possibilities. So either red shorts or blue shorts. And we know the probability of picking a red on the first, so this is my first kind of pick, is 3/5 because I have 3 red shorts and a total of 5 shorts. And I also know that this here would be 2/5 because the numbers on my branches always add up to 1. And so then I would have my next second kind of selection here, where I can then pick red, blue, or red and blue. And so this probability here of picking a red, I know I've already picked a red shorts already, so I have 2 reds left. And because I've picked a short already out, I've only got 4 left. So this would be 2/4, which is equal to 1/2. And of course, the other branch would be 1/2 as well, because they add up to 1. Similarly, for this over here, we know that I've picked out a blue shorts, so I've only got 1 blue shorts left and a total of 4 shorts remaining. So this would be 1/4 and 3/4. And so we do the same thing for our third kind of selection as well. So I won't go through that just because of time. But because we're picking our 3 shorts, we would draw kind of this diagram for 3 different selections. We can then label out our outcomes. So whether we have red, 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 blue, and red, blue, red, etc. And then find the probabilities of each of that. So to find the probability of red, 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 I multiply the probabilities along this branch in pink over here. So 3/5 times 1/2 times 1/3. And the same thing, if I talk about my red, red, blue, so red, red, blue here, I would have 3/5 times 1/2 times 2/3. So multiplying across my branches over here. And we do the same thing for all of our outcomes and all of that. So in the last 5 minutes or so, we'll finish up with talking a bit on combinations and probability. So in terms of combinations, we use the concept of factorials. So we know n factorial is the same as n times n minus 1 times n minus 2, etc. So what this means is if I want to find the factorial of 5, we have 5 factorial, which is represented by an exclamation mark. And that is equal to 5 times 4 times 3 times 2 times 1. So all numbers that are less than or equal to that number multiplied together. And so in terms of our combinations formula, we know that we can represent it as NCR, where N is the total number of objects we have, and R is kind of what we're choosing out. So that is equal to N factorial divided by R factorial times N minus R factorial. And so we'll look at an example to kind of use this formula as well. And so the reason that combinations as formula here is important is because this is used quite a fair bit in terms of probability and discrete binomial distributions. So in terms of combination, we know that we don't care about the order. So let's just say, I want to choose a particular number of people from a lecture. It doesn't matter kind of the order that I pick the people in. We just want to find how many different groups I can actually choose. Doesn't matter if I choose this person first and then this next person after that. As long as I choose 3 different people, that's okay. So I want to find how many ways I can do that. So again, this is important because we use this a bit in our discrete probability, which refers to our binomial distribution. So if you guys remember, for our binomial distribution, we have this formula over here, which is saying probability that X is equal to something is equal to our combination of nx multiplied by p, which is the probability of success, raised to the power of x multiplied by the probability of failure, so 1 minus p, to the power of n minus x. And we multiply it by this because this combinations here over here tells us how many ways we can obtain the result. How many ways of obtaining the result? Over here. And so now we'll look at this example to kind of finish off this lecture over here, which is a bit on combinations. So I've got this question over here that's saying Daniel is a professional shooter. On average, he hits the bullseye 40% of the time. During a competition, he has 5 shots and needs to hit the bullseye at least 3 times to win. What is the probability that he will win? So looking at this, the first thing that I need to kind of check is that what kind of distribution I have. So I noticed that I've got a constant probability. So I've got a probability of success P as 0.4 consistently. So that doesn't change depending on whether he hits the bullseye of the first shot or not. So we've got a same probability of success throughout all of these different shots. And we've also got n shots, so n different kind of trials of that. And I also know that I've got so probability of either hitting or missing the bullseye. So there's 2 different kind of possibilities there. So from all of that, I know I've got a binomial distribution from this. So I can use my binomial distribution formula that we just saw before up here to solve this problem. So we know that n is the number of shots. So n is 5 shots in total, and we want to find the probability that he wins. So I'm going to let my variable, let's let x be equal to the number of bullseyes that Daniel hits. So number of bullseyes. Yeah. And I know that x is a binomial distribution with n is 5 and p is 0.4. So then to find the probability that he wins, we get, that's the same as the probability that he hits the bullseye at least 3 times, because he needs to hit it at least 3 times to win. So that's the same as saying x is greater than or equal to 3. And so this would be equal to the probability that x is equal to 3 plus the probability that x is equal to 4 plus the probability that x is equal to 5, because there's 5 shots in total. So he can either hit 3, 4, or 5 bullseyes to then win. To figure this out, we can use our formula above over here. So this would be equal to our NCR. So N is 5, R is whatever number that we have over here. So this would be 3 or NCX as well. So 5c3 multiplied by p, which is 0.4 to the power of x, which is 3, times 1 minus p, which is equal to 0.6 to the power of n minus x, which is 5 minus 3, so it's 2. And I have then 5c4 multiplied by 0.4 to the power of 4 times 0.6 to the power of n minus x, which is 5 minus 4, so it's 1. Then plus the probability, plus the combination of 5 multiplied by 0.4 to the power of 5 and multiplied by 0.6, so 1 minus p, to the power of n minus x, which is 5 minus 5, which is 0. So I'm able to put all of that onto my calculator to then get a final answer, which is 0.3174. So yeah, that's how we would do something like this. So for our combination style questions, we know that first thing I need to do is to check what type of distribution I have before kind of deciding which formula I would need to use. But yeah, so that was all for this part, and that's the last part of our session. So you guys didn't get any breaks in between the different parts of the lecture. But yeah, so that's all for the content part. So thanks so much for coming as well. If you guys have any questions, feel free to stay back and I'm happy to answer any questions that you guys might have. I hope this lecture has been helpful in helping you guys do a bit of revision for some fundamental Unit 1-2 concepts. And yes.
Perfect. Thank you so much. I just wanted to thank Margery really quickly for all her time and effort that she's put into putting this together for you guys. And I'm just going to pop a couple links in the chat really quickly before you go. The first one that I'm going to put in is just to our website. So the KIS website, sorry, that was not the right link. The KIS website, so that you can check out our other events that we have. We've got some free ones posted on YouTube, so go and check those out. And then this other link that I'm just going to send through is if you want to give any feedback about today's event. So yeah, thank you all for coming. And if I'm not getting any questions coming through, so I'm happy to wrap up there. And as I said, please send me an email if you would like a recording of this to watch it back, because I know we covered heaps of stuff today. All right. Thank you, Margie.
Thanks.
Bye.